Okay, I think we'll get started. So welcome to the first lab in the Machine Learning for General Chemistry sequence. Today we're not actually going to be doing any machine learning, but we're going to look at jargon associated with evaluating machine learning models. So some of the key ideas here are to look at a visual representation of machine learning results and numerical quantifiers. So these are ways that a chemist would learn about whether the model is a good one or not. And this could be influenced by what the data the model is trained on, or the model itself. And so it's really important to be able to characterize how good the model is. Now we're going to look specifically at actual versus predicted plots, and we'll be using this throughout the whole sequence for the machine learning course, and then some residual plots, which are a really important thing to get a handle on, and it could be perhaps new to you here, so we'll talk about that. And then three important numerical quantifiers out of many that professional chemists doing machine learning would look at. And that is mean absolute error, mean square error, and R-squared. And you're probably familiar with R-squared if you've been doing some general chemistry or general biology and you're plotting some data and looking at how well those data fit the line. So we're going to focus in on the plots and then these two measurements of error. So what is done after a model is run is we plot the predicted value versus the actual value on a test data set that the model is working with. And in an ideal case, the model would, every value, here I've got three values, the blue with the capital letters. We might have 1,000, 10,000, a million, 10 million, whatever. All those would be plotted here. In an ideal model, they would all fall on this 45-degree line here indicated in red. This means that the predicted value is exactly the same as the actual value. Now, of course, in real life, that is never going to happen, and there's going to be some kind of scatter about that 45-degree line, and we want to be able to recognize that and evaluate the nature of that scatter and do so both with pictures and also quantitatively. So what one does then is one looks at the difference between the predicted value and the value that it should be, or the actual value, and that's indicated by these green lines here in lowercase letters, A, B, C. So then what does is creates a new plot called a residue plot that shows how that shows the differences, just plots the differences. So A is different from the line by this, B is by this, and this. So we get scatter about a zero line. And in an ideal model, all the data would fall right on that zero line. Now what this does is it helps display the data in a way in which we can recognize both scatter, so how big is the scatter about the zero line. So if we have if we're just scattered equally about the zero line, then our model is accurate, but it might not be very precise if that scatter is big. Now, what we could also notice in here are systematic trends. So maybe the data go down, or they go up as you move along, or the scatter expands or contracts. Those are different indicators of what might be going on. We're going to see two examples, one where it goes down and one where it goes up, as systematic deviations from the actual value. And that would be, of course, undesirable in a machine learning model. Now, where do these measurements of error come in? Well, we take these values, here, 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 and in mean absolute error, we take the absolute value and then divide by the total number that we have. So in this case, 3. So we normalize versus the size of the data set. And then in the mean square error, we square all of those. Now, why are we doing these operations? Well, we need these to be all positive numbers. So let's take, for example, B and C. Notice how they both are deviating from the line, which means there's an error. But if we were to simply add them together, they would cancel and eliminate that error, which would not be a good measurement of how well this model is doing. So we need to make everything positive. Now, what about the choice of that? Why absolute value versus square? Well, when you square a number, it's going to accentuate the bigger numbers versus the smaller numbers. So mean square error is better for situations where you might be very concerned about outliers, because an individual outlier will carry more impact than a number of ones that have small deviation as compared to the mean absolute error. If you're in a situation where the outliers can be taken care of and they don't matter that much, then the mean absolute error might be the better indicator. So it all depends on the setting of your data. All right. Well, with that, let's go to the lab and let's walk through it. I'll walk through it with you for the most part, but also I really encourage you to pause the video, play around with it, really get to understand it. It's not a very long lab, so you've got plenty of time to think about things as you go along. Okay, so let's go to, let me get up on the screen here, collapse OBS, and let's look at our Chem AI Street introductory lab sequence. I just want to double check. Yeah, I think I'm good. Okay. Now, if you don't know where this is coming from, go back to the introductory video for this mini course on AI and machine learning. You will find a video walking through the installation of this. But we can get there with our, if we go to the course page, which will be linked in the description, you can see all the stuff needed to get started. And again, I won't spend time here because of the previous video there. So let's bring this down, and then let's look at our first lab, which is the basic residue lab. So up pops our program, and before we get into it, let's go through the lab here. And again, we'll not be performing any actual machine learning. I've just made up some fake results of machine learning. Now, when we go on to the other experiments, we'll also be using fake results through this whole mini course of four labs, but they will all be doing real machine learning on those fake data. And so the ideas we learned today will carry over when we're evaluating those models. Now, our learning objectives here are to get a feel for both the pictorial or graphical representation and the numerical representation. So absolute predicted versus actual, and residual plots, along with mean absolute error and mean square error. Just some background on how the machine learning takes place is you typically need a large data set, and those data are broken into subsets, a training set and a test set. The model trains on the training set and then gets applied to the test set to measure these errors. So we'll see a plot of how well it does against the test set. Now, one thing that's really counterintuitive when you're first learning machine learning is that you would think the more you train, the better. But that's actually not true. There's usually kind of a sweet spot on how much the model trains, and that brings up this concept of overfitting, which we'll talk about a lot through the lab sequence. Overfitting will actually train the model on some of the noise that's in the particular training set that has nothing to do with the physics or chemistry. And so then when it's applied to the test set doesn't have that particular noise, and the values are actually worse than if it wouldn't have trained as much. So part of the art and science of machine learning is dealing with the test and training sets and how much you train each of those sets. And so we'll see that not in this lab so much, but as we go forward, and we'll recognize that in the metrics that we're learning about today. So that's one of the important reasons we're learning these metrics. Okay, so kind of said this a couple of times now: actual versus actual versus predicted, and then residual plots. we're going to look at 4 different scenarios. The ideal model, of course, is what we're comparing to. That would be everything falls exactly on the 45-degree line. We're going to look at a negative deviation case, a positive deviation case. So these have systematic errors, either under-predicting or over-predicting the values. And then we're going to look at a high scatter case where the model is accurate but very imprecise, and then a low scatter model where this would be the best situation for this case. We'll see that play out in both the actual plots and the residual plots, and also in the quantitative metrics here. Okay, well, let's get into the experiment. So I've got this loaded. We're going to load our first data set. And so if you could navigate to where you put your data sets, mine is here. So I'm going to do the negative deviation as we're told here in the lab procedure. And here come the data. And we can see down here, things are doing pretty well. We're scattered about the 45-degree line. But then as we progress with more with larger values of our actual property, whatever properties we're looking at, we start to under-predict. Our prediction falls short of what it should be. Now, when this transfers over to the residuals, we see a systematic downward trend in the residual. And this shows that we have our model is not accurate. And so we have some kind of systematic error. So this would be undesirable. We can look at the qualitative metrics. I'm going to move that just a bit. The qualitative metrics, absolute error, square error, and then this R squared. And notice here, this R squared is not actually too bad. We're taught that R should be between 0 and 1, with 1 being, a perfect fit. And here, if you were to just look at the R squared, you'd see that's a pretty decent R squared value. But clearly, the graphs are indicating a systematic problem with this model. All right, I'm going to let you do the positive deviation. See if you can make a prediction of what you're going to see before you load the data set and then load it and compare it. One thing you can do is start filling out a chart here. So we've done the negative deviation, so we can list our mean square error of 8.02, mean absolute error, or mean square error of 94.73, and then our R squared value. And so you'll have a nice table there when you're done. So go ahead and do the positive one. I'm going to pick up here with the high scatter one. And lo and behold, we see this scattered about the 45-degree line. We see no noticeable systematic trend here, both in the predicted versus actual and in the residual plots. So this model is in principle accurate, but it is very scattered. Now in the residual plots, I want to flag for you the importance of looking at the scale. So the way these are plotted is it's plotted so that it shows you the most action with the data. So every time this comes up, take note of the scale. And so we see this distribution here. When we go to a low scatter, you're going to see it's going to look visually like this, but the scale will be much smaller. All right, well, let's look at the mean absolute error. Highest one so far, mean square error, highest one so far, and a really terrible R squared value. So not a very good model here. Okay, well, let's move to the last model, which is the low scatter model. Here we see much more tightly clustered. We see scatter being, again, looking similar to the previous one, but let's look at the scale now. The scale is smaller. And then the quantitative metrics much better. So the lowest errors by far so far, and the best R squared value. So get that recorded in your table. And then take some time and discuss these results. Try to compare and contrast the different data sets, what the plots and the numerical values are telling you about those data sets. And then once you're done with that, you can look in this section and compare to what's written here. See if you agree or disagree. See if you've got more things to say. If there's something in here that you didn't say, kind of go back and see if you can see where that's located in the data. All right, after that, start thinking about Some of the things that a chemist would be worried about, well, we've talked about the interpretation. The other thing we want to learn as we move through this series is some of what machine learning can and can't do. So a good developing, at least starting our understanding of where machine learning is applicable in chemistry and where it might not fit very well. And then starting to pick up on some of the best practices, and that started today here with utilizing multiple different metrics to understand how the machine learning model is working. And there are many, many more than that is not really necessary for us to go into, but in more advanced level, you would have lots of different ways to statistically analyze your results. We want to look for systematic biases. We kind of saw that in today's lab. And then ultimately, you want the model to handle the robustness of your particular data set so that it's not thrown way off by outliers, or it's actually focused on the right properties that you're interested in. Okay, then write up a conclusion, and there are a couple of reflection questions here that you can think about as well. All right, well, thanks for doing the first lab, and we'll see you on the next lab.